Jupiter's moon Europa is a fascinating world with a salty, subsurface ocean.
Europa, one of Jupiter's moons, is home to a vast ocean that contains twice as much water as Earth. This incredible discovery was confirmed by NASA, with the James Webb Telescope detecting water and revealing the presence of an ocean beneath Europa's icy surface. Such findings reshape our understanding of space and the potential for life beyond Earth. Earth is unique in having 71% of its surface covered by water, a vital element for life. However, it's easy to forget that other parts of the solar system lack this abundance. NASA's findings on Europa open new doors in the search for extraterrestrial water and life, significantly advancing scientific knowledge. Jupiter, the largest planet in our solar system, is remarkable for its sheer size and gravitational pull. With a diameter of 143,000 kilometers, Jupiter is 11 times larger than Earth and boasts a volume over 1,431 times greater. Its immense gravitational force, 2.5 times stronger than Earth's, contributes to its dynamic atmosphere, famous for phenomena like the Great Red Spot and swirling cloud bands. Among Jupiter's many fascinating features is its collection of 80 moons, 57 of which have been officially recognized by scientists. The remaining 23 await identification and naming by the International Astronomical Union. Of these moons, the four largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei and Simon Marius, who discovered them in 1610. These moons are not only historically significant but also massive, exceeding the size of known dwarf planets, and standing out as some of the largest celestial bodies in the solar system. Europa and Ganymede, the two innermost Galilean moons, exhibit a unique orbital resonance, with Ganymede completing one orbit for every two of Europa's. Io, another Galilean moon, completes 4 orbits in the same period. This intricate relationship adds to the allure of Jupiter's moons and their role in shaping our understanding of the solar system. Jupiter's moon system is a fascinating display of harmony and variety. Beyond the well-known Galilean moons, Jupiter boasts an impressive collection of moons. Astronomers estimate there are around 100 irregular moons with diameters larger than 1 kilometer and an additional 500 smaller retrograde moons as small as 0.8 kilometers in diameter. Due to their weaker gravitational pulls, these irregular moons often have unique, irregular shapes, highlighting the diversity within Jupiter's moon family. Each of Jupiter's moons is distinct in size, composition, and geological features. Ganymede, the largest moon in the solar system, is a true giant and a captivating target for scientific study. However, Europa, the 4th largest of Jupiter's moons and the 6th largest in the solar system, stands out for its scientific significance. Europa's most striking feature is its remarkably smooth surface, the smoothest of any solid body in the solar system. Unlike other celestial bodies, such as Mars with its rugged terrain, Europa's surface lacks large craters and rough landscapes. This smoothness, interrupted only by a few low hills that rise just a few hundred meters, points to an active geological past that has reshaped its surface over time. Europa is also tidally locked, meaning one side of the moon constantly faces Jupiter. This phenomenon occurs due to the gravitational interaction between the moon and the gas giant. Unlike Earth's moon, whose far side always faces away from the Earth, Europa's rotation is synchronized so that the same side perpetually faces Jupiter. This tidal locking creates unique surface conditions, with the leading hemisphere, facing the direction of Europa's orbit, experiencing stronger tidal forces, while the trailing hemisphere, facing away, feels weaker ones. The gravitational pull from Jupiter stretches and squeezes Europa as it orbits, causing its core to flex under the strain of these tidal forces. This continual deformation generates internal heat, which plays a critical role in maintaining the moon's subsurface ocean and its potential to support life. Europa's dynamic nature and unique characteristics make it one of the most intriguing objects in the solar system for exploration. This process, known as tidal heating, plays a crucial role in sustaining Europa's geological activity and shaping its distinctive features. Compared to Earth's moon, Europa is slightly smaller but far more complex. It is believed to have a layered structure with an iron core, a rocky mantle, and a vast ocean of salty water beneath its icy crust, an astonishing discovery. The ocean's depth is estimated to be between 40 and 100 kilometers, far exceeding the depth of Earth's seas. In fact, Europa's subsurface ocean is thought to contain about twice the volume of all Earth's oceans combined. Since water is essential for life, the presence of such a massive reservoir of liquid water makes Europa an exciting candidate for further exploration and the search for potential life. But how do we know Europa has an ocean beneath its icy surface? Observations and studies from multiple scientific disciplines provide compelling evidence. Data from the Hubble Space Telescope and, more recently, the James Webb Space Telescope strongly indicate the existence of a global ocean beneath Europa's ice. Spectroscopic analysis has been especially vital in understanding Europa's composition, surface, and the connection to its hidden ocean. By studying the light reflected or emitted by Europa across different wavelengths, scientists can gather detailed information about the Moon's chemical and physical properties. These spectral fingerprints reveal that Europa's surface is primarily composed of water ice, confirming the presence of abundant frozen water. This combination of tidal heating, a vast subsurface ocean, and a frozen surface rich in water ice makes Europa one of the most intriguing locations in the solar system for exploring the possibility of extraterrestrial life. The discovery of water ice on Europa is significant, as it suggests a potential connection to a subsurface water source. Spectroscopic analyses have revealed that Europa's surface contains not only water ice but also salts, which likely originate from the ocean beneath the icy crust. These salts could have been transported to the surface through processes like cryovolcanism or other geological activity. Moreover, spectroscopy has detected organic molecules on Europa's surface. These carbon-based compounds are the building blocks of life, making their presence particularly exciting for astrobiology. Understanding the unique spectral fingerprints of different materials is critical, as it allows scientists to map the composition, distribution, and behavior of substances on Europa's surface. By analyzing the sunlight reflected from Europa or heat emitted by its surface, scientists can obtain detailed spectral data that reveal the chemical makeup of the Moon. These readings, collected by instruments aboard spacecraft that fly by or orbit Europa, are compared to theoretical models and laboratory experiments to interpret the findings accurately. In addition to surface analysis, important insights into Europa's interior have come from studying its magnetic field, particularly through NASA's Galileo mission. The detected magnetic field strongly indicates the presence of a conductive fluid beneath Europa's surface. The most plausible explanation for this is a subsurface ocean of salty water, which interacts with Jupiter's powerful magnetic field to produce the observed magnetic signature. By examining the magnetic field's strength, direction, and variations over time, scientists have gathered valuable data about the ocean's depth, size, and salinity. These findings also provide clues about how the ocean behaves, including potential currents and their interactions with the overlying ice shell. Beyond confirming the ocean's existence, magnetic field studies help researchers understand its dynamics, offering insights into the interactions between the liquid water, the icy crust, and the Moon's external environment. This information is critical for advancing our understanding of Europa and its potential to harbor life. Understanding Europa's magnetic field provides valuable insights into how the Moon functions and its internal structures. Magnetic readings reveal information about the conductivity and composition of materials beneath the surface, shedding light on the connection between the subsurface ocean and Europa's rocky core. These measurements also help scientists explore geophysical processes, such as tectonic movements and hydrothermal vents, which may result from interactions between the ocean and the Moon's interior. In addition to magnetic studies, thermal devices and sensors play a critical role in investigating Europa's surface and the temperature of its subsurface ocean. These advanced tools record heat signatures and monitor temperature variations, offering essential data on the energy transfers between Europa's vast ocean and its icy crust. By examining these thermal characteristics in detail, scientists refine their models and deepen their understanding of heat flow and stability within Europa's dynamic environment. Thermal readings provide valuable clues about the ongoing processes beneath Europa's surface. However, surface imaging and mapping are equally important for studying the Moon. Using cutting-edge, high-resolution imaging techniques and precision mapping methods, researchers analyze Europa's complex fractures, ridges, and other geological features, which may offer critical insights into the hidden ocean below. Detailed images allow scientists to map Europa's surface, uncovering its mysterious landscape. By documenting the locations, sizes, and arrangements of these features, they can better understand the Moon's intricate interior. Each new image and geological discovery adds to the growing body of knowledge about Europa's hidden processes. Moreover, mapping and imaging are essential for planning future missions. These techniques not only enhance our understanding of Europa's surface and its potential to harbor life, but also help identify the most promising areas for further exploration. Identifying key locations for future exploration on Europa is vital for upcoming missions. While current efforts rely on tools like the James Webb Space Telescope, the future may involve deploying robotic explorers, or even humans, to Europa's surface. To prepare for this, scientists must gather as much information as possible from afar. By studying specific areas of interest, such as regions with active geological processes or thinner sections of the icy shell, researchers can prioritize the most promising sites for detailed investigation. These insights are paving the way for future missions to Europa. One highly anticipated project is NASA's Europa Clipper, scheduled for launch in October 2024. The mission's primary objective is to determine whether Europa's subsurface ocean could potentially support life. Unlike a lander, the Europa Clipper will orbit Jupiter and perform approximately 40 to 50 close flybys of Europa, adjusting its flight path to capture detailed readings and observations of nearly the entire Moon. The mission aims to identify areas below Europa's icy crust where conditions might be suitable for life to survive and thrive. While it is not designed to detect life directly, it will focus on assessing the Moon's habitability. Scientists are already certain that an ocean of liquid water exists beneath Europa's surface, and the spacecraft will conduct a thorough investigation to determine if this environment could support life. The Europa Clipper mission is equipped with an advanced scientific payload designed for an in-depth study of Europa. The spacecraft will carry a range of high-tech instruments to gather critical data, enabling comprehensive research into the Moon's surface and interior. These tools will measure the Moon's magnetic field, monitor surface temperatures, analyze the composition and thickness of the icy crust, and provide a detailed overview of Europa's fascinating features. Essentially, the mission will build on the data we've already collected from afar but with much closer, more precise observations. The Europa Clipper will perform 44 flybys of Europa over its 3.5-year mission, at altitudes ranging from 25 to 2,700 kilometers. Each flyby will offer scientists the opportunity to gather fresh data, explore new perspectives, and refine existing information about the Moon's potential to support life. These close encounters will help researchers uncover what lies beneath Europa's icy surface and provide a better understanding of this intriguing Moon. The Europa Clipper holds great promise for advancing our knowledge of potentially habitable worlds within our solar system, and it could help answer profound questions about the possibility of life beyond Earth. There may be an entire ecosystem hidden beneath Europa's frozen surface, but we'll have to wait for the Europa Clipper mission to provide the definitive answers. What do you think? Is it truly possible? Share your thoughts in the comments below, and don't forget to like this video and subscribe to our channel for more exciting updates. See you next time.